All right, so I was going to start you guys on our new unit about waves. So this is our second to last unit. We're getting pretty close to done. And there's a couple basic terms to waves that are, some of them are going to be kind of familiar. Things like period, which we talked about with our oscillation, simple harmonic motion. Frequency, we talked about that in terms of the omega, the angular frequency, but it's still a frequency. Velocity is still a velocity, okay? And now we've got two real new terms, wavelength and amplitude. And these, well, I guess actually this even shows up in our simple harmonic motion too, doesn't it? Just basically when we talked about it with the spring, the amplitude was basically how far you stretched it out from the relaxed length, right? And how much it vibrated away from that relaxed length, that was the amplitude. And with a pendulum, right, the amplitude is basically how high it went, its height that it swung back and forth to. So you can see there's a lot of similarities between the waves and simple harmonic motion, which is why I've stepped us through in this way, simple harmonic motion, then waves. Because it turns out waves are really just oscillations that are traveling at a speed, which is why they get that velocity, okay? It's no longer an angular speed. This is actually a straight line speed. This wave is actually going to travel some distance as it goes, right? So if I look at it, I have a string here, just happen to have one in my pocket, why not? So if I have this, I don't know if you guys can see this or not, but maybe the slinky is a better idea. If I have this and I stretch it out, you can see that this wave is going to travel along the length of the slinky here at a speed, right? So it's going to go from here to there. If I let it go, you can see maybe even like a wave motion to it. Maybe the string would work better after all. You know what? My son's got a snake here. I'm going to use a stuffed snake. Even that'll work, right? Okay, so if I do this and I send a wave along it, there you go. That worked out remarkably well. So there you go. You can actually see the wave is traveling along there. There it is. It goes from me to there. Okay? So it has a speed that it travels this way. Okay? So they definitely still have a straight line velocity like we talked about all last semester. So maybe we should just start gesturing with the snake, right? We have wavelength, amplitude, wave velocity. We have the frequency and the period. Let's talk about what all these things mean. Okay, frequency has a new, relatively new unit to go with it, hertz. Hertz are an interesting thing. Hertz are the same as 1 over seconds. Okay, so it's inverse of our period. And that really is the formula for this. So if we wanted to figure out our frequency and the period of our wave, how often it takes to go back through one full cycle, right? So let's talk about that first, actually. Maybe that would make more sense. Let's call this our t-axis for time, okay? In fact, I better put this as little t because it's not number of periods. Okay, and here's our y-axis, that's in meters. Okay, so this wave is going back and forth like this over some time, okay? So how do we find the period of this thing? Well, the period is a time of a wave. It's the period of one full oscillation. And if you remember from a spring or a pendulum, one oscillation was when it gets back to the same point going the same direction, right? So if I pull this thing back, right, it's going to go up and then it's going to come back down. So it's going to go, if I pull it, extend it this way, it goes back up. So that hasn't reached an oscillation yet. It's just gotten to its maximum point, right? And then it comes back down to that same point, and then it comes, and it's about to go back up again. The minute it's about to go back up again, that's one full oscillation. Well, the same thing is true for a wave. So same place, going in the same direction, okay? So if we start at a really easy spot place here like this is called, the peak of the wave is called a crest, okay? And the bottom of the wave is called a trough. Two important terms to know about waves to start with, okay? So if we want to pick out a place to start our timer, well, those are two great places to look. And since my second trough is actually running off the board, I'm going to choose a crest here, okay? Another good place to choose is where it crosses zero, but if your wave is shifted up or down and it's not exactly on zero, that gets to be less of a great place to look, okay? So it's really easy to pick out our peak. So I would suggest you guys do that. Use a peak, a crest, or a low point, a trough, okay? Choose one of those as your starting point for anything to do with waves, okay? So if I look from crest, my next crest is all the way over here. So since this is my time axis in seconds, the time it takes to get from here over to the next one, that's my period. The time it took to go from where it was back to where it started in the same direction, that's my period. So on this graph, where I have my y versus my time here, okay, I would go from 1 second is where my first crest appears, and my second one goes to 5 seconds. So my period for this thing is going to be a total of 4 seconds. Okay, so that's my period. What would my frequency be? Well, here's the formula for frequency. So frequency, it turns out, is just 1 over your period. All right? And vice versa. If you know your frequency and you want to find your period is 1 over frequency. They're the inverse of each other. Okay? So you can see why now this is expressed in hertz, it's 1 over seconds. Okay? So if my period was my period was 4, my frequency would be 1 over 4, or a quarter. Okay? I would have 0.25 hertz over 4 seconds. So it would be 0.25 hertz would be my frequency. So why do we do this? This seems like an overly complicated way of looking at things, doesn't it? Well, it can be, but it can also be remarkably useful. So if we talk about things in hertz, what does that tell you? It tells you how many waves have gone by you in 1 second. So that's kind of cool, isn't it? My voice is in thousands or maybe tens of thousands of hertz, right? So if that's the case, let's say it's 5,000 hertz, just for giggles, okay? So if my voice, the sound waves coming out of my mouth are going at 5,000 hertz, that's how many waves are going to go past you, how many oscillations you're going to have in 1 second. So if I'm speaking at 5,000 hertz, 5,000 waves have passed your ear in 1 second. So that's kind of cool. So you can see now why that could be a useful term, okay? And a period, again, period is just time. You already know time, but it's the time of one full oscillation. And again, we already kind of know that from our simple harmonic oscillations, okay? So let's move on. Let's look at some other stuff in here, okay? So I'm going to erase this, so if you want to write this down, well, it's on the equation sheet, but I'll also get rid of it here, so you can always go back and rewind and look at that, okay? So I'm going to leave that labeled, okay? I'm going to leave the troughs and the crests labeled. I'm going to leave the same numbers on here, but now I'm going to look at something else. I'm going to change my axis. This is no longer going to be time. This is going to be distance, okay? So I'll call this x in meters, just like this is y in meters, okay? So now we can talk about two different things. First off, very first term up here, wavelength. What the heck does that mean? It's the length of one full wave. And what is one wave? It's an oscillation, really. It's an oscillation of some sort, a back and forth motion like we talked about with our simple harmonic oscillators. So back and forth, back to the starting point. Well, again, if we want to use this as our starting point, a crest was our starting point, so we go back to a crest. That right there, from that crest to the next crest, would be one full wave, okay? Same thing could be true of a trough. You could measure from trough to trough, or if it's a nice and centered wave where 0 is, the crossing point, the midpoint of the wave, you go from 0 to 0, whatever is easiest. I think that it's best, again, to look for crests and troughs because no matter what wave or what orientation or, where this thing is shifted to, you're still going to have your crests and your troughs that are really easy to find, okay? So this, from that point to that point, is one full oscillation in distance. We've measured it in distance now, okay? So again, we start at 1 for the first crest. We go to 5 for the next crest. So if that's in meters, now our wavelength on this, in this case, would be 4 meters. We'd have one wave that would take 4 meters for a full wave to go by, right? That would be the length. If you stopped time, you can measure that wave. That's how long that wave would be. So that is one measurement of a distance. There's a second distance to measure, though, isn't there? Because we've got an x as well as a y. The wavelength is basically the x measurement, okay? What's the y? Well, the y measurement here is going to be from the crest to the midpoint, right, or the basically the midpoint of the wave, right, the resting place of the wave, right, the equilibrium point. From there up to the peak would be a distance. So that distance we label A. That's our amplitude, the height of the wave, okay? Now, could you measure to the trough? Sure, you can absolutely measure to the trough. You can go from there down to the trough. That is still the same amplitude. Now, it's the opposite direction, so an amplitude is really a magnitude, okay? It is a magnitude, basically, of the y, okay? And actually, really, the change in y, okay? That's basically your amplitude. I just drew another delta, but we can change it to an A. Okay, so there we go. So amplitude is basically just your magnitude of your change in your y. how far above the midpoint of the wave or the equilibrium point of the wave, or how far below. Either one is acceptable, okay? And it's also measured in meters. So if I look at my y, I go from 0, that's our midpoint. I'm going to go up 1, 2 meters that way. Let's just check on the other side and make sure our wave hasn't shifted. How far down does it go? Well, 1, 2 meters down. So our amplitude for this guy is 2 meters. And we don't give it a plus or minus because, again, it's both. It is both plus and minus. It's a magnitude, all right? So wavelength, the actual length of one full wave or one full oscillation, and amplitude is basically the height above its midpoint or its equilibrium point or below it, okay? The frequency is just basically how many waves go past you in 1 second. The period is how long it takes for one wave to pass by, okay? So the only thing we haven't talked about is the wave velocity, and again, that's just the time it takes for the wave to pass by. It could, and it's measured in meters per second. So this is just like our previous one, right? There's nothing particular to one wave going past. This is just the speed of any single point on that wave. How fast is that point going? It's going to be measured in meters per second, okay? So that's kind of the basics of it for all the pieces of the wave. But what the heck is a wave? What is a wave?